And the last talk before the coffee break will be about polarization, diffusion, space-time uncertainty by failure.
Thank you to Sabina and the other organisers for organising this meeting and for giving me this chance to talk. I'm going to tell you about work. Speak up.
Yeah.
Tell you about work that I've done with Carlo Contaldi, co-workers Carlo Contaldi and Lydia Philpott at Imperial College. So the work that we did was based on a very simple strategy for constructing models of quantum gravity phenomenology. And I'm going to tell you what that strategy is. And it's based on a very simple idea which underlies quite a bit of quantum gravity phenomenology, which is that dynamical quantities such as particle trajectories and other physical variables will be subject to small, quasi-local, random fluctuations due to their microscopic interaction with the background spacetime, whose structure is uncertain at Planckian scales. Uncertain in some way for some reason, whether due to quantum fluctuations, space-time foam, fuzziness, non-commutativity or discreteness, whatever. So there's some uncertainty at Planckian scales, and that affects the dynamical variable. So as I said, much quantum gravity phenomenology is based on this idea, but I'm going to add an extra assumption. And that extra assumption is that the effect of this uncertainty is Lorentz invariant. Okay, so here's the strategy. The first thing to do is identify a space of states for the dynamical quantity, whatever it is. Then consider a random walk on this space of states in its hydrodynamic limit. So what we're going to do is think about Brownian motion of this state in its space of states. And this is, as everyone knows, some kind of diffusion drift process governed by a Fokker-Planck equation, assuming that that process is continuous. So I'm going to make that assumption. It may be that the fluctuations are more violent than continuous. If they're discontinuous, then you would have to describe it via some Boltzmann equation. But we're going to assume continuity, that the kicks are small enough that the process is continuous. You then work out how Lorentz transformations act on that state space, and you constrain this diffusion drift process on your space of states to be Lorentz invariant. Okay, and I'm going to just give you examples of this to show you how it works. All right, there are advantages and disadvantages to doing this. The first disadvantage is that it's phenomenology of phenomenology. By the end of the talk, you'll know what I mean by that. It's at least 2 steps away from a fundamental quantum gravity theory, so we will have no handle whatsoever on the fundamental parameters from physics. There is no physics in this talk, in fact, at all. The second disadvantage is that it's very, very general. So if we find some observational signature, if we make some prediction using these models, and our experimenters and observationists go out and find these effects, then it could be claimed as evidence for any quantum gravity theory that predicts Lorentz invariance. So that it's very general. It doesn't distinguish between fundamental theories. Okay, what are the advantages? So why bother? What are the advantages? Well, it's extremely easy to do, as you'll see. And the second advantage is that a lot of quantum gravity phenomenology violates Lorentz symmetry, as we've heard in this meeting. So it's good to have alternatives, especially as data constrains us on Lorentz symmetry violations more and more tightly. Okay, so the first example of the strategy is that of a massive particle propagating through Minkowski spacetime. So the first thing to do, so this is the strategy. First, identify the space of states, and that is S, which is the product of Minkowski spacetime, so the particle has a position in spacetime, times the mass shell, so it has momentum. H is the hyperbolic, 3-dimensional hyperbolic space, the Lobachevsky space. So the coordinates on our state space are denoted as X, capital A, that's position in space-time, momentum P, where P squared plus M squared is 0. That's it. Okay. Now, the most general diffusion drift process on this state space is given by the following 2 things: current and a continuity equation, as is familiar. And this form of the current was derived in complete generality by Sorkin. He just analysed the most general stochastic evolution on a manifold of states. And it has this form. There are parameters which are DAB, which is a symmetric positive 2 tensor on your manifold of states. N, which is a density, an equilibrium density. And UA, which is a vector on this manifold of states. And then the continuity equation is just the usual thing. Okay, so that's it. That's step 2. Step 3, how to Lorentz... Yeah, please.
Yeah. If N is the equilibrium density, why is it inside derivatives? Is it something that also comes on? Just if you go back a step.
Yep. So if N...
rho over N.
Yeah, so if rho is proportional to N, then this vanishes. That's good. So it goes.
Okay, but N can vary.
So d rho by dt will be equal to 0.
Okay, but does N also have an evolution equation, or N?
No.
No. Okay.
It can depend on P. That's the point, but it depends on P in equilibrium.
Ah, thank you. Yeah.
Okay. Well, how do Lorentz transformations act on our space of states? Well, we know how they act. They act in the usual way. Positions transform in the usual way. Momenta transform in the usual way. And the diffusion process will be Lorentz invariant if the diffusion tensor D, the drift vector U, and the density of states are all Lorentz invariant, that this equilibrium density are all Lorentz invariant, and the time parameter in which this process takes place is proper time along the world line of the particle, the massive particle. If you add further conditions that the process is translation invariant, it doesn't matter where in space-time you are, the process is the same, and relativistic causality, thus as the world line of the particle is constrained to be within its own light cone, then these conditions are incredibly strong. And the only possibility for this process is the following. This is, I've turned the probability density into a scalar just by scaling by the square root of minus g. The square root of minus g is just the metric. G is the metric on our space of states, which is, so this is just 1 in fact. It's 1 on space-time and it's whatever it is on the mass shell. There's one parameter k, it's a positive number, the diffusion constant. This this Laplacian is the Laplacian on the mass shell. And that's it. The m is the mass of the particle. So you can derive this from the conditions of Lorentz invariance, or prime-pair invariance because it's translation invariance, and relativistic causality. And it's just a one-parameter family of models. So it's diffusion, like diffusion on the mass shell, which drives a secondary random process in space and time. So there's no diffusion in space-time, if you like. There's diffusion on the mass shell, but and then the particle moves in space and time according to how the momentum, the randomly set momentum. Okay. So momentum is going to diffuse. So some initial distribution, which is peaked in momentum, is going to spread. And that means that particles initially at rest in some cosmic frame will spontaneously accelerate in vacuum. There's no drift in momentum. As you can see, there's no drift term here in momentum. So this drift is only in space-time. And that's due to the fact that there's no invariant vector on the mass shell. So that UA vector on the mass shell actually is 0. There's no Lorentz invariant vector on the mass shell. Now there's a huge amount of phenomenology that you can do with this. You can apply this to neutrinos, to cosmic ray primaries, and look for such effects and constrain the single parameter of the model. Okay, and you can also apply the strategy to massless particles. The momentum space is now not the hyperbolic space, but the cone, p squared equals 0. And there, the one difference is that there is an invariant vector, which is p mu itself. So Q mu is the Lorentz invariant on the cone. This Lorentz invariance forces the process on the cone to be one-dimensional. So the diffusion process and the drift occur only in the energy direction. And it's governed by two parameters, two numbers now. The diffusion constant, which governs how much it spreads, how much the distribution in energy spreads, and one drift parameter, which notice is CP violating. It's a drift towards the red or the blue, depending on whether your parameter is positive or negative. And again, there's huge amounts of phenomenology you can do with this. So spectral lines will spread, and they'll spread with in a very particular way set by the model, and they'll also drift either to the red or the blue. All right. So the second model I want to tell you about is photon polarization. So again, we just apply our simple strategy. We identify the state space, and we assume that you can model one of the free streaming photons from the CMB, as a classical particle with a momentum k, and with the polarization given by some complex 4-vector AU. So we're modeling the polarization classically. And that polarization vector is transverse to momentum, it's normalized to 1, and it has a gauge freedom that if you take a vector A primed, which is just A but shifted by any amount proportional to the momentum, then that's the same polarization state. So and the normalization overall phase of A mu are not physical either. So if you choose a frame in which K mu has coordinates k, 0, 0, k, then A mu you can choose to be 0, A1, A2, 0. A1 and A2 are just complex parameters, where A1 squared plus A2 squared is 1, and the overall phase is not physical. So the state space of such complex two-dimensional vectors is CP1, it's just the block sphere. Here's a picture of the block sphere. And on the block sphere, the equator, the states around the equator are the linearly polarized states, and the poles, the north and south pole, are the left and right circularly polarized states. Step 2 is to write down a general diffusion process on this two-sphere, and it's exactly the same thing. We just use the same equations as a current and a continuity equation. We have to choose a two-tensor, which is positive and symmetric, an equilibrium, density, and a vector. So that's step 2. And step 3 is we identify how Lorentz transformations act on this state space. And it turns out that they act as polar rotations. So you can just, so A mu is a 4-vector. It transforms as a 4-vector under Lorentz transformations. You can just trace through what that Lorentz transformation does to A1 and A2. And it turns out that what it does is it rotates the block sphere around the north-south polar axis. Okay. So to make our diffusion process Lorentz invariant, we have to choose this two-tensor, this density, and this vector to be invariant under these rotations. Okay. Unfortunately, there's a lot of them, many functions worth of choices. So in particular, DAB, for example, you can think of that as a metric. It's a metric on this two-sphere, and you can imagine it squashed this way, or it's rugby ball, oblate, prolate, all sorts of funny shapes you can have, so long as it's invariant under these polar rotations. So there's a lot of choice for this, a lot of choice for this, a lot of choice for this, and that means that there are really too many phenomenological parameters to be particularly useful. We can, however, say one thing, which is that circular polarization can result from an initially linearly polarized distribution, either by drift or non-spherical diffusion. So if you imagine that the distribution is concentrated on the linearly polarized states on the equator, and if this drift vector has flow lines which just go from the south pole up to the north pole in a circularly symmetric way, then this distribution will gradually drift towards being left circularly polarized. So you can generate circular polarization by these models. However, there's just a lot of parameters, so it's not good phenomenology. However, if we restrict to linear polarization, if we just say, well, maybe there is no CP violation. Maybe the underlying physics is not going to be able to generate circular polarization from initially linearly polarized photons. Then the state space is just the circle, it's just the equator. And then we regain phenomenological control of the model. Because now we've got our space of states is just the circle. The process has to be invariant under rotations of that circle. And we deduce the following. This is the unique rotation invariant diffusion process on the circle. Lambda is affine time along the photon world line. Beta is just the angle around the circle. D is a positive constant. C is another constant. And this is manifestly Lorentz invariant because lambda is Lorentz invariant, and theta, so a Lorentz transformation just adds a constant to theta. If we transform from affine to cosmic time, in other words, time in some laboratory or observatory frame, then T is related to affine time by the energy. And we get this equation, this is now laboratory time T. And we see that for observations, the rates of diffusion and drift are frequency dependent with this very specific dependency. So it's inversely proportional to the energy. So the higher energy photons will diffuse less and drift less. So the lower energy the photons, and the more this effect will affect them. And note again that the Lorentz symmetry that we've assumed is only invariant under the continuous component of the identity in the Lorentz group, because this drift term here explicitly breaks CP invariance. All right, so that's a proposal for what polarization, the distribution of polarization of C and B photons does as they travel through space-time to get to us. And we can look for those effects. And if you're lucky enough to have Carlo as your colleague, you can ask him to help you with this. And he produced this incredibly beautiful plot here. So I don't know much about this, but what Carlo did was a Monte Carlo Markov chain parameter estimation for the two parameters, which are the total rotation of the polarization, which we call chi, and that's proportional to the, did I get that the wrong way around? Yeah, I think that might have to be C and that might have to be D. So it depends on the time of the cosmic time that has elapsed since the photons were produced, and is inversely proportional to the frequency. And polarization depth, which again is a measure of how much the overall polarization fraction has decreased because of the diffusive effect. So let me just, right. So there are two sets of data here. One, the orange and yellow are all of the relevant data are included, and the green and the blue are the data minus the data from an experiment called Quad. And you can see that there's some disparity between them. However, the two inner regions do overlap. So the all polarized data is consistent with no effects. That's a bit disappointing. So this origin here is no polarization rotation and no diffusion. So that's that point. And the data is consistent with that. However, in the literature, these two sets of data are inconsistent with each other. So this overlap between the favored region of the old polarized data and the data with quads taken out. In the literature, those don't overlap, and so there was reported a big kerfuffle about the fact that there was a disparity between them. But because our parameters our effect is frequency dependent, it seems that the frequency dependence reduces the tension between these two sets of data. Yeah.
Sorry, Faye, you see, there's no diffusion. That's what you say. You find the effect.
It's consistent with no diffusion. Yeah.
Yes, but well, of course, there are the errors aside from this. So you know that how. If you had diffusion, what would mean for you?
It would mean that a peaked distribution of polarization would spread, and it would mean that the total polarization amplitude would decrease.
No, but I mean for the Lorentzian values, what it would mean? That's my question. For your underlying assumption, would it mean anything or?
I'm not sure I understand your question.
I mean, where does your diffusion come from?
Her diffusion, she's not testing Lorentz invariance. Her diffusion is Lorentz invariant.
Ah, okay. But that's what I mean. So the absence of diffusion, could it open a window for not? I mean, in other words, suppose that you have a Lorentz invariance violation. Right. How it would come up in this?
It doesn't say anything about it whatsoever.
Ah, okay. Okay. Thanks. That's. Thank you.
Okay.
Or a Lorentz modification, by the way, not necessarily violation. You may have a
right. This doesn't address it.
So you cannot say. You say.
Yeah, can't say.
Thanks.
Okay, so I don't want to stress these numbers because, as I say, we have no physical control over what the numbers should actually be from physics. But just to be, my notation is broken down as well. So D is actually little d, and little d is actually c. Sorry. So this is the diffusion constant. This is the drift constant, and you can bound them from Carlo's calculations. But I don't want to attach any significance to these numbers, whether they're big, whether they're small, because we have no physical model that will produce these effects for us.
Penny, I'm kind of confused, sorry. But, so those numbers are coming from observation?
Yes.
So
They're
with
observational
current
constraints.
observation you have these constraints?
Yes, they're observational constraints. From
How is
CMB
that
polarization
really in the sense that the polarization of the CMB photons is affected in many ways between the CMB and us.
Indeed. So
You have
that's all.
you have many effects that can enter. I mean, it's a complicated. You don't know exactly.
That's all models by these CMB fast Boltzmann-Einstein equations, which are indeed solved with all the physics in there. So that's how these plots are made.
But assuming that there are no B modes, right? That must be, or is that assumption not there?
We assume that there are no primordial tensor modes. However, this polarization rotation can generate them, even if there are none to start with. So the fact that they're not measured so far is part of this constraining. It's part of the constraints that the data put on these parameters. So yeah, if this drift were too big, then it would generate B modes, correlation, BB correlations, and TB correlations, which.
No, what I'm saying is, if I take, for example, the blue data, which you said seems to indicate a 1 sigma, 2 sigma effect of
yes.
drift, it could have two explanations. Either there are B modes there, or primordial B modes, or there is this effect of the drift that you're talking about.
Right, so there are degeneracies.
There's a degeneracy,
right? Yeah. Okay. So I don't want to attach any significance to this fact, but a posteriori, there is a lessening of the tension between these two sets of data. If for our model where the frequency dependence is specifically is specifically inversely proportional to the effect is inversely proportional to the frequency.
So presumably these Monte Carlos take that into account. I mean,
yes, they do. That's right.
So this is already factoring in possibility.
Okay, let me go on. All right. So if we forget the drift for a minute, which is just this overall rotation of the polarization vector around the circle, if we just consider the diffusion alone, what it does is it spreads an initially peak distribution in polarization. So it has the same effect as a decoherence of the quantum. If you treat photon polarization quantum mechanically, and introduce decoherence, then this diffusion of the classical photon polarization state is the same effect, has the same effect phenomenologically as decoherence in the quantum states polarization state space. And such decoherence due to quantum gravity effects is widely studied, but it's not usually Lorentz invariant. So usually there's some environment. The environment has a particular frame. It's the rest frame of the matter producing the decoherence. Here, this is decoherence, which is Lorentz invariant. So it's decoherence due to space-time fluctuations themselves, and there's Lorentz invariant. However, so it's not usually Lorentz invariant. However, there is this paper, which is called Probing Possible Decoherence Effects in Atmospheric Neutrino Oscillations, in 2000. And these authors compared the two-flavor neutrino oscillation model with the decoherence model against data from Super Kamiokande. And one of the parameters in their decoherence model could be set so that it gives exactly the same Lorentz invariant model that we would get if we applied our strategy, so the 1, 2, 3 strategy for producing the Lorentz invariant diffusion process. If we apply that to the block sphere state space of two flavors, just treating it classically, getting the diffusion equation, blah blah, that would give us exactly the same suppression effect as this, as the decoherence model considered by these authors. Okay. And let me quote from them: the two cases, in other words, the two-flavor neutrino oscillation model, the favoured particle physics explanation for atmospheric neutrino data, and this Lorentz invariant decoherence model they seem surprised, right? So they seem surprised and treated it maybe almost as a joke, right? They appear to be almost indistinguishable within errors. So I don't think it's an exaggeration to say that, at least in 2000, there was as much reason to believe in a Lorentz invariant decoherence as in neutrino oscillations to explain atmospheric neutrino data. I don't know what the situation is now. I probably, yes. What's the situation now?
Yeah, I was going to point out that,
yes.
this result was sort of superseded by Super Kamiyokande's paper in 2004,
right,
which prefers a mass-induced oscillation scenario over this particular decoherence.
This particular one. I was afraid of that.
Nevertheless, the surprise they expressed is justified. In 2000, things were murky.
I agree, yeah.
Okay, so let me conclude. So there's a simple strategy. You've seen how simple it is. I mean, I gave you everything. I gave you the whole details of everything. Every single, these 3 steps. And literally step 2 isn't really a step because you just write down this general, these 2 equations for this general process of stochastic evolution and manifold of states. It's already there for you. So this simple strategy can model the effects of Lorentz invariant, of the uncertainty in space-time at the Planck scale, be it fluctuations, fuzziness, discreteness, or whatever. In general, we can get CP violating effects, for example, generating circular polarization from a distribution of polarization that's initially completely linearly polarized. But we have there's no physics, as I said, there's no underlying physical mechanism that we can point to say, yes, well, we do expect that kind of effect. These diffusion effects are the same as, they have the same outcome, as far as phenomenology is concerned, as Lorentz invariant decoherence. And we could then apply it. We can apply this to other polarized distributions, for example, electrons and magnetic fields, wherever they occur, and they occur a lot. So we can do Lorentz invariant decoherence phenomenology applying to these to other situations in which we have polarization. However, we need physical models now that produce such effects in order to get a handle on how big the phenomenological parameters should be. While those numbers for the constraints on the polarization, diffusion and drift, are they just way too tight? Or would you expect them to be a lot bigger from physical considerations? We can't answer those questions until we have models. Those models, I would expect, in the first instance, to be phenomenological models. You'd have some model for some space-time background which is uncertain at the Planck scale in some way, and then you would put fields, maybe massless fields, on such a background and see whether you can find evidence that you get these diffusion and drift effects. So that's what I mean, that this is phenomenology of that phenomenology. So we don't have that, we don't even have that phenomenology, the middle layer of phenomenology, let alone full quantum gravity. Okay, so that's what I mean, that we're at least two steps away from fundamental quantum gravity. So we require, to do this middle step, to do this middle piece of phenomenology, we need a model of space-time that's uncertain at the Planck scale, and also Lorentz invariant. So that's necessary to generate these kinds of diffusion drift processes. And there is such a thing. So you can model space-time in a Lorentz invariant way as a discrete object called a causal set. Causal sets are the basis of an approach to the problem of quantum gravity, which has been championed particularly by Raphael Sorkin, and it fits the bill. So one way forward in trying to build the more physical models that we'll need to justify this sort of hyper phenomenology is to do stuff on causal sets, put matter on causal sets and see how it behaves. And I'll end there. Thanks.
Yeah, coming back to your very first transparency, you said Raphael classified all diffusion processes on the state space. Yeah, for particles. That's half-dimensional manifold that you write down. It's not quite the space of states. It still has this gauge freedom that's given to you by Newton observations. So the state space for relativistic particles is 6-dimensional. Now, my question is, it's not obvious to me that classifying the most general diffusion process on that sort of redundant space, which still has this gauge freedom, is equivalent, if you classify it and then you project it down to the real phase space, gives you the same answer as classifying the most general diffusion processes on the real configuration of space of states. Because you make some restrictive assumptions on how the diffusion process should proceed in directions which are not physical.
Sorry,
along the gauge lines. Is that a problem, or is that obvious?
What's the gauge invariance?
Reparameterization invariance along the world line of the particle. This constraint, p squared plus m squared equals 0, generates a flow on that 7-dimensional manifold by a Hamiltonian flow. And points on this flow line are considered to be physically equivalent.
There is
So when you say three components momentum, you say
But that's a 7-dimensional manifold.
Yeah, but what do you mean by that depend on the particle, right? You need 3 coordinates, the time, and 3 momenta. You cannot reduce this further.
Sure, you can reduce it further. That 7-dimensional manifold is not reduced phase space. It's the constraint hypersurface in the 8-dimensional space, which is the cotangent bundle over Minkowski space. And your first-class constraint, single one, which reduces the 8 degrees of freedom by 2.
No, but look, that I don't understand. Let's forget about bundles and that stuff. Take S as a phase space, okay? So all she's saying is,
it can't be phase space because phase space has even dimensions.
Right, it's
This
not
is
a
a
phase
7
space.
no, it's not a phase space
It's not a
because
phase
you still have this condition, for sure. But I mean, you surely need 7 numbers to pin on the dynamics of a particle in phase space.
No, you need,
Usually not time. Usually we don't sign.
Right, here I'm
Yeah,
time.
that's true.
Here
it's
I'm
like
time.
a relativistic particle plus a clock.
Yeah, that's true.
Yes. Yeah.
So you make some assumption about how the clock also makes a diffusion.
No.
And
No, time is fundamental. So,
time is fundamental.
yeah.
No, but then he's right. You're right.
Yeah. I would like to, I mean, it's very interesting what you're doing. But to call it decoherence, I just want to draw, I mean, let me focus on the analogy with the decoherence model, because I can tell you my personal
It's more
view.
than an analogy, so...
No, but that's where I'm coming. When we have, in these models, which by the way, these are Lindblad models, so it was not the Montagnier, it has been developed in '84, you know, these are Lindblad models with an environment that respects complete positivity and whatever, there are certain axioms, this particular class. There is a density matrix of a quantum system of matter, in the analogy in the neutrino, and there is a fundamental property. CPT is violated because the thing is irreversible, right? I mean, you can prove that the trace of rho square is less than 1, and therefore you have evolution of pure states to mixed. You see, that's what I want. In your case, there is nothing quantum. You're looking at the density. That's what I would like to draw the difference, right? And you have CPT preserved because you have Lorentz. Your CPT is
No,
not.
the diffusion process is not.
Pardon?
The diffusion process is not time reversible.
Precisely.
It's a
Then,
diffusion.
correct. So, but then, so you have a CPT violating situation when you quantize the system. I mean, the analogy, your rho is a classical concept, am I right?
Yes, that's right. But,
Theirs is quantum, is a density matrix.
right,
That's all I'm.
but when you make the predictions about what you actually observe in terms of loss of
Okay.
numbers of neutrinos of a certain flavor, it's exactly the same.
No.
Yeah, yeah.
But that's what I mean. I mean, it's an analogy. It's not one is a. But what I'm coming back to this, and now I understand what you are finding in the CMB spectrum is that you do not have CPT violation there. That's all you're finding. The fact that you found, am I right or am I wrong in this? So the fact that your CMB data are consistent with zero diffusion, as far as I understood, means that they are consistent with CPT invariance. Am I right or
Yes, that's true.
That's your conclusion, right?
Consistent with it, but
Yeah,
who knows what
I
better
agree.
data will
There may be
show
evidence
us.
in the future. Okay.
So at the moment, it's consistent with no effect of any sort. I mean, not just this, but there are other models which predict the rotation of polarization, which have a different frequency dependence. People have looked for that, and that's again, it's consistent with no such effect. So, yeah.
So, on the average, your diffusion process conserves energy, if I understand correctly, but energy can be violated in individual events and individual fluctuations.
No, not if there's a drift. So if there's a drift, it doesn't even preserve it on the average. So that's right.
Good. So consider your case with zero drift.
Okay, zero drift, yes.
Zero drift.
So no, on the average, it doesn't preserve it either. So that's so
Even with zero drift.
even with zero drift,
It does not conserve energy.
right?
So is one way to constrain the parameters of the model to look at sensitive tests of conservation of energy?
Possibly. I mean, we did our first completely crude estimation bound that we put on this diffusion parameter for the massive particles was just to say, here's a box of hydrogen. It's not heating up.
Right.
Right. So that was But I'm sure people could do much better than we did. Just that was very crude. So yeah.
Okay. Second quick question: if we gave you, if somebody gave you a different state space, for example, the one of DSR, you could apply the same analysis.
I don't know the exact. I mean, do Lorentz transformations act on
Yes.
the state space?
Yes.
Presumably, yeah. So if you have a manifold of states, then you have some transformations that you want to preserve, then yes, you could do.
So presumably you get a different flow on the block sphere, right, for related transactions. Presumably.
Okay. So it's interesting to discuss that.
Yeah.
Yeah, I just wanted to come back to this first question that has been asked. So why are you considering the second dimensional space? Because I think the question is extremely important. What did you mean when you say time is physical here?
Everyone knows Minkowski spacetime is just an approximation to right? So let's take the spacetime in this room lasting for a particular physical time. Right? So, and the Minkowski spacetime that in this model is just some approximation to that. Right? It's a modeling of that. So, but that's the thing I have in mind. And then to describe the state of a particle, you need to give its coordinates in space and time and its momentum. That's it.
Can I ask a question as well? Why didn't you look at circular polarization? Because it's extremely difficult to generate circular polarization with any mechanism, except actually doing something extreme. So I understand there's also flexibility, but did you actually look at that?
All we did was notice that you can generate circular polarization from initially uncircularly polarized distributions. But to actually have a model, you would have to make some choice of this metric on the two-sphere, some choice of this density of state, some choice of this vector, and we have no reason to choose make one choice over another choice. So that's.
I mean, on the other end there is this thing. I mean, okay, suppose we see TV disparity violating things. That's actually not that weird. If we saw circular polarization in CME, it would be a scandal. You know, it would be quite difficult.
It would be great.
It would be a scandal. What?
I find circular polarization because it's basically scattering. Scattering produces linearized polarization, not circular polarization. So you need something like a drift from linear to circular polarization to get something like that.
But we have there's no physics, right? It's just that you could have it, and it doesn't violate Lorentz invariance.
It violates time reversal invariance, so it must be physics. I mean, this thing, if you see it, means that CMB spectrum violates time reversal. Am I right?
Yes.
That's what you. I mean, the diffusion. That's exactly what it does.
Yeah.
And the question is, electromagnetism doesn't. So it must be. That's an important thing. If you see it, it's something more than electromagnetism. That would be quantum gravity. Could be something else.
Yeah. If we saw it, if we saw it, then
Good. Since you said that the analysis was rather easy, do you think it would be feasible to repeat this analysis in a deformed special relativity scenario? And do you have an intuition of if the results would be changing?
I don't have any intuition. That was Lee's question.
Okay,
it sounds, from what Lee said, possible. So but I don't have any intuition about what to do.
So if I understand the analysis correctly, you could in principle, or perhaps you haven't done it, use the energy dependence on the polarization to disentangle gravity waves from the effect you're looking at.
Yes.
Is that correct?
As far as I know, there is. I'm not saying that you couldn't produce a different model which would produce this particular dependence on the frequency. But as far as I know, there is no other model that does so as of now.
I mean, there's always the J-rules. For example, you can change one parameter and another combination, and you get the same thing. When you get these plots, you're basically marginalizing over that. So it's a statistical statement when you play it.
Okay. Gravity wave does not produce a energy dependence in the polarization. The polarization would be there for everything.
But you're not looking at different energies here. It's different. So it's kind of basically.
But
so you could in principle.
Yeah. So we would like data on polarization that's binned by frequency.
Yeah.
Very detailed.
That's what I'm saying.
Small, bins as small as possible, so that we can. That's what we'd like.
Any more questions? We have to cut this off. Okay, let's stop. Thank you.